Hello everyone, in this video we will cover the section 12.6. In this section we will see standard forms of the equations of cylinders and some special quadric surfaces. So the theoretical definition of a cylinder is that in three-dimensional coordinate system it is a surface that consists of all lines called rulings and that are parallel to a given line and pass through a given plane curve. So to determine a cylinder in three-dimensional coordinate system, at the beginning we have to define a line and we have to define a given a plane curve. Okay, for defining a plane curve in three-dimensional coordinate system, one of the variables x, y, and z should be missing from the equation to define a plane curve in three-dimensional coordinate system. For example, let's sketch the graph of the surface. Z is equal to x squared. So we notice that the equation of the graph, the equation of the surface z is equal to x squared does not involve the variable y. We don't have the variable y in three-dimensional coordinate system for the equation z is equal to x squared. An equation involving the variables x, y, and z states a surface. So this means that in a vertical plane with equation y is equal to k, parallel to the xz plane, intersects the graph in a curve with equation z is equal to x squared. In the xz plane, if we don't consider the axis y, in the xz plane z is equal to x squared is z is equal to x squared. Let's show here. This is the z axis, x axis and y-axis. In the xz plane, it is a parabola. Z is equal to x squared is a parabola in this form. X squared is always positive, therefore we sketch the parabola in this form. So we don't have any information for the variable y. For the surface, every point can be written as we consider the variable x and we don't have any information y, so we write y directly. And for the last component, we write x squared according to the given equation in the example. This is x squared. So this is the general form of a point on the surface given here. So how can we sketch the graph of this surface in three-dimensional coordinate system? So after sketching the graph of this plane curve, this is actually a plane curve, which is the one of the conditions to define a cylinder here. So now we will define a line. So how can we define? This is determined by moving the plane curve along the variable which is missing in the equation. Y is not in the equation z is equal to x squared. Therefore, we move the graph of the plane curve which is z is equal to x squared along the y-axis, and we get this graph. Okay, by moving along the y-axis in this form. So we have a parabola, the same parabola, actually they are parallel to each other. So we obtain a graph which is an example for the cylinder. So we obtain the graph of the surface and the lines will be parallel to the y-axis since the variable y is not in the equation. All lines here, which is the second condition to define a cylinder in three-dimensional coordinate system, it is called ruling of the cylinder. So all of them are parallel to each other, and the baseline, the basic line, is the y-axis. For example, let's sketch the graph of another equation, let's consider y is equal to square root of x, or x is equal to y square, such that from here, you know, square root of x cannot be negative, therefore we consider y is bigger than or equal to 0. We can consider this one or this one, they are equal to each other. So in three-dimensional coordinate system, it can be sketched as, this is the x-axis, this is the y-axis, and this is the z-axis. X is equal to y square is a parabola, you know, by considering the positive side of the variable, the axis y, the y-axis. Or we can consider directly the graph of the root function. If you remember, it should be in this form, in the xy plane. Z is not in the equation, you see, therefore the line of the cylinder will be the z-axis. Actually, mainly we will move the graph of the plane curve like this. This is the graph of the root function, y is equal to square root of x, or x is equal to y square with the positive side of the y-axis. Actually, we continue from here to complete the plane curve, just if we consider x is equal to y square without giving the condition written here for the y-axis. But we have y is equal to square root of x, or x is equal to y square, and by moving this curve along the z-axis like this, so we obtain a cylinder such that the plane curve is x is equal to y square, and the lines are parallel to the z-axis. This is another graph for another cylinder in three-dimensional coordinate system. If one of the variables that I said, x, y, or z, is missing from the equation of a surface, then the surface is a cylinder. The most known equations for a cylinder in three-dimensional coordinate system are given here. X squared plus y squared is equal to 1, or y squared plus z squared is equal to 1, or x squared plus z squared is equal to 1. So, you know, we don't have any information here for the variable z, which means it is a cylinder and its plane curve is a circle. You see, this is the equation of the circle actually in the xy plane like this. And by moving this circle along the z-axis, since we don't have any information for the z-axis, so the direction of the cylinder will be the z-axis, and the lines are parallel to the z-axis. You see, after moving the circle infinitely many times here. And similarly, y squared plus z squared is equal to 1 is a circle in the yz plane, since we don't have x here. And by moving this circle along the x-axis, we get another form of the cylinder in three-dimensional coordinate system. So you can sketch easily the graph of the last one yourselves. This is your homework. Please sketch this graph, and if you have any question for this, please send your questions to me. Okay. So generally, a quadric surface is the graph of a second-degree equation in three variables, x, y, and z. The most such equation can be given in this form. Okay. You know, generally, the equation of a plane is given by ax plus by plus cz plus d is equal to 0. Here you see you don't have any second degree of the variables like x squared, y squared, or z squared. Therefore, it is in the linear form, which means it states a plane geometrically, graphically, in three-dimensional coordinate system. And you know the general form of a line in three-dimensional coordinate system. If you remember the symmetric equations, it can be given as x minus x0 over a, y minus y0 over b is equal to z minus z0 over c. This is completely different from the general form of a quadric surface, and you can see the difference between them. We don't have any second degree of the variables x, y, and z, but when we have second degree equation for the variables x, y, and z, so we will have another special surface in three-dimensional coordinate system, which is called a quadric surface. So by applying necessary transformations like translation and rotation, if you remember from calculus 1, this is the section 1.3 actually. So this equation can be transformed into the one of the standard forms written here. Can be in this form or in this form. Okay. So by assigning a special conditions for this general form, we obtain some important surfaces in three-dimensional coordinate system. For example, so if second degree equation involving the variables x, y, and z, if it is in this form written here, so you see we have always plus for the signs of the terms in the on the left hand side of the equality. X squared plus y squared plus z squared is equal to 1 is the most simple one. X squared plus y squared plus z squared is equal to 1, which is actually the equation of the sphere with radius 1. Okay, and you see if the numbers a, b, and c are equal to each other, so the ellipsoid becomes a sphere. Generally, if you have different numbers for the denominators in here, we obtain an ellipsoid in this form. You see the graph of ellipsoid, which is similar to the sphere, but since we have different numbers in the denominators, so we have ellipses. Actually, if we take intersection of this graph with vertical and horizontal places, if you intersect this graph by a vertical plane, so we will obtain an ellipse, okay, like this. Or if you intersect this plane with a horizontal, this graph with a horizontal plane, you will obtain another ellipse. So the second special surface is called cone. Its equation is given by z squared is equal to x squared plus y squared. Z squared is equal to x squared, which is the most simple one of this special surface. Z squared is equal to x squared plus y squared. So horizontal traces are ellipses. How can you obtain the horizontal traces for this graph? So we intersect this graph with a horizontal plane. Okay, if you intersect this graph with a horizontal plane, for example like this, so you will obtain an ellipse. This is the intersection of the plane and the graph of the cone, and you will obtain a horizontal curve for the cone, which is an ellipse. Okay, or by writing any value for z since the horizontal plane can be stated as z is equal to k, if you remember. If you write any number for z, you will obtain an equation of the ellipse. And vertical traces can be obtained by intersecting the cone with a vertical plane. So it will be an hyperbola. If you remember, a hyperbola in two-dimensional coordinate system can be given graphically in this form. Okay, this is the graph of the hyperbola. Y-axis, x-axis. So the equation of the hyperbola can be given as x squared minus y squared is equal to 1, or the most general form can be given as x squared over a squared minus y squared over b squared is equal to 1. Okay, this is the graph of the hyperbola. If you intersect the cone vertically like this, you will obtain a hyperbola. Okay, like this. So these are the intersection of the graph of the cone with a vertical plane. Similarly, another special surface is called the elliptic parabolate, whose equation is given here. You should understand the difference between the equations of the special surfaces. You see we have x squared plus y squared plus z squared, but here we have z squared is equal to x squared plus y squared. Actually, by writing z squared to the right side, you will get 0 is equal to x squared plus y squared minus z squared. Okay, this is the difference between the ellipsoid and cone. Similarly, we have z is equal to x squared plus y squared. If you don't have the number 2 for the power of the variable z, this is the difference between the cone and elliptic parabolate. You will get another surface which is called the elliptic parabolate. Horizontal traces can be obtained by intersecting the graph with a horizontal plane. If you intersect this one with a horizontal plane, so you will obtain an ellipse. Okay, you will obtain an ellipse like this one. For example, if we consider this one, so we will have an ellipse for the intersection of the horizontal plane and the elliptic parabolate, its graph. And vertical traces are parabolas. If you intersect the graph of the elliptic parabolate with a vertical plane like this, okay, vertical plane, so you will obtain parabolas. So the variable raised to the first power indicates the axis of the parabolate. You see we don't have the number 2 for the power of the variable z, therefore the graph of the elliptic parabolate lies along the z axis, and algebraically you can see the traces of the graph of the elliptic parabolate by writing, for example, 0 for x squared. We get z is equal to y squared, which is a parabola, you see, and so on. Another special surface is called the hyperbolate of one sheet, whose equation is given here: x squared plus y squared minus z squared. So if we write minus instead of plus in the equation of the ellipsoid, we obtain another special surface which is called hyperbolate of one sheet. Okay, Horizontal traces are ellipses if you intersect this plane, this graph with a horizontal plane. Similarly, you will obtain an ellipse. Okay, horizontally, you cut this graph with a plane, with a paper in three-dimensional coordinate system, and you will obtain an ellipse. Okay, because you know, the equation of the horizontal plane can be given as z is equal to k, which is parallel to the xy plane, or you can consider directly z is equal to 0. If you write 0 for z, you will obtain the equation of an ellipse. Therefore, algebraically also we can say horizontal traces are ellipses. Vertical traces are hyperbolas, can be obtained by cutting the hyperboloid of one sheet with a vertical plane. A vertical plane. For example, you see graphically actually vertical plane is a parabola. Okay, vertical plane is a parabola. This is the curve which is the intersection of the vertical plane with the graph of the hyperboloid of one sheet. So here you see we have minus for z square. Therefore, the axis of symmetry corresponds to the variable whose coefficient is negative. Another form, for example, another form can be given as minus x squared plus y squared plus z squared is equal to 1. So this is the hyperboloid of one sheet. This is another form, hyperboloid of one sheet, and we have minus for the coefficient of x squared. Therefore, the symmetry axis will be the x-axis for the hyperboloid of one sheet. Therefore, its graph will be in this form: x-axis, y-axis, z-axis. So we sketch an ellipse at the beginning, since vertical traces are now ellipses. If you should be in this form. Okay. Namely, the symmetry axis is the x-axis. Actually, we have an horizontal hyperboloid of one sheet, since we have minus for the coefficient of x squared. Similarly, if you write x squared minus y squared plus z squared is equal to 1, so its graph should be x-axis, y-axis, z-axis in this form. Okay, the symmetry axis is the y-axis. And another special surface is the hyperbolic paraboloid, given by z is equal to x squared minus y squared. If the coefficient of y squared is minus in the equation of the elliptic paraboloid, so we have another surface which is hyperbolic paraboloid. Just by changing the sign of the coefficient of the variable y squared, we obtain a different graph for the surface in three-dimensional coordinate system. Therefore, when you write an equation of a surface in three-dimensional coordinate system, you should be careful to get the true surface. So horizontal traces are hyperbolas. If you sketch a horizontal plane, okay, and if you intersect this plane with the graph of the hyperbolic parabolate, so the intersection curve will be a hyperbola. You can see also from here horizontally we have an hyperbola which is actually parallel to the xy plane, because if you write any number for the variable z, you will obtain a general equation of the hyperbola in the xy plane in two-dimensional coordinate system if you write any number for z. So for the vertical traces, namely can be in this form, namely we write any number for the variable y because it is parallel to the xz plane, which means we should write any number for y. So we obtain a parabola z is equal to x squared, or if you write 0 for x, and the vertical plane can be also in this form, okay, by writing any number for x or 0. So we have z is equal to minus y squared, which is another parabola in the yz plane. Therefore vertical traces are parabolas, and you can determine the traces on the graph after understanding the intersections of the vertical and horizontal planes with the graph of the hyperbolic parabolate. For example, you can see the horizontal curve here, and vertical traces can be shown like this. Okay, this is the intersection of the graph of the hyperbolic parabolate with the vertical plane which is parallel to the xz plane. Okay, and also we have another parabola you can see from here. Okay, this is on the yz plane. This is on the yz plane. Can be obtained by writing any number for x which is parallel to the yz plane. Okay, and the last one is called the hyperbola of two sheets. Can be obtained by writing the equation written here, or another form. The most known form of the equation of hyperbola of two sheets can be given x squared plus y squared minus z squared. Actually we multiply this equation by minus is equal to minus 1. Just we change the sign of the number 1 on the right hand side in the equation of the hyperbola of one sheet, and we obtain hyperbola of two sheets. We have two sheets. We have the same term on the left hand side, x squared plus y squared minus z squared, but here we have minus 1 for the right hand side. Okay, if we have plus 1 we will obtain hyperbola of one sheet. If we have minus 1 we will obtain hyperbola of two sheets. And from here you can see if you write 0 for z, so we will get x squared plus y squared is equal to minus 1. Cannot be possible. Okay, therefore we obtain two sheets. If you write 0 for y, so we have x squared minus z squared is equal to minus 1, or z squared minus x squared is equal to 1, which means we have a parabola in the xz plane. Okay, so horizontal traces are ellipses. If you write any number for z bigger than, and writing to the right side, you will, if you get a positive number, actually we have x square plus y square is equal to a number which is positive, so we obtain an equation of the ellipse. Therefore, if you intersect the graph of hyperbola of two sheets, so you will obtain an ellipse. You see, if you intersect this graph vertically, so you will obtain a hyperbola. Okay, like this. You will obtain an hyperbola. Okay, for example, use traces to sketch the quadric surface with equation x squared plus y squared over 9 plus z squared over 4 is equal to 1. By looking at the table here, so it is corresponding to the general form of the ellipsoid, because we have always plus for the coefficients of the variables x, y, and z. And we have a number here like this. Therefore, it is actually an ellipsoid. And writing zeros for any two of them for the variables x, y, and z, you can obtain the limit points like this. For example, 0, 3, 0 can be obtained by writing 0 for x and z. So we can obtain 1 if you write 3 for y, or minus 3, which gives the left border, the left limit point of the ellipsoid on the y-axis. And similarly for the z-axis, if you write 0 for x and y, we get 0 z squared over 4 is equal to 1. So z can be plus 2 or minus 2, and we obtain the limit points of the ellipsoid, and you can sketch the graph of the ellipsoid. And you can understand the traces by writing 0 for one of the variables x, y, and z. If you write 0 for z, you will obtain an equation of the ellipse in the xy plane. X squared plus y squared over 9 is equal to 1, which is an ellipse in the xy plane, you see. And similarly, you will obtain another ellipse on the xz plane, and you can sketch the graph of the ellipsoid by using the traces like this. You will move the plane curves of the surface, and you will obtain the graph, moving to the left side and to the right side, or moving to up or to bottom. Another example, use traces to sketch the surface z is equal to 4x squared plus y squared. Okay, this is actually 2x squared plus y squared, and we don't have any we don't have the number 2 for the power of the variable z when we look at the table. So it is corresponding to the equation of the elliptic parabola. Therefore, the graph should be in this form. So z is equal to 2x squared plus y squared will be in this form. Z is the symmetry axis of the ellipsoid, and when we write any number for z, we obtain an equation of the ellipse in the xy plane. And by moving this ellipse along the z-axis by considering its value according to the equation, you see when we increase the values of x and y, so the variable of the z also will be increasing from this equation. Therefore, the size of the ellipse will be increasing along the z-axis when we move it to up. Okay, and you see we don't have any graph for the negative side of the z-axis, since it cannot be negative. Okay, And similarly, z is equal to y square minus x square. When we look at the table, y square minus x square is corresponding to hyperbolic parabolate. Okay, actually, hyperbolic parabolate, x square minus y square, or y square minus x square. And when we write any number for x, so we obtain parabolas on the yz plane, you see. Or when we write any value for y, we get z is equal to minus x square, which are another parabolas, such that the parabolas is downward, you see. And when we write any value for z, you will obtain y square minus x square is equal to some number, which is the equation of hyperbola in two-dimensional coordinate system, like this. And by moving them separately, for example, we move the parabolas on the yz plane along the x-axis, and we move the graph of the parabolas on the xz plane along the y-axis, and we move the graph of the hyperbola in the xy plane along the z-axis. By combining them, so we obtain the graph of the elliptic graph of the hyperbolic parabolate. Okay. And similarly, you can see this example easily. And this is another example. Identify and sketch the surface. So you see, generally, this equation cannot be compared in the current form in the table, but by doing some operation, we get a similar equation in the table, dividing by minus 4. So we have minus x squared plus y squared minus z squared is equal to 1, because when we write the constant to the right side, we have a negative number, but dividing by minus 4, we obtain 1. So this is the hyperbola of two sheets. We have plus for the coefficient of y square. If you look at the table here, for the coefficients of two of the variables, we have minus. For one of the variables, we have plus for its coefficient. Therefore, it is actually a hyperbola of two sheets. And you see we have plus for y square. Therefore, the symmetry axis will be the y-axis. And when we write any number for z square, for example, we have hyperbolas in the xy plane, and similarly we have hyperbolas when we write 0 for x on the yz plane. So the surface has no trace in the xz plane. If you write 0 for y, you see we will have negative value for the left side and positive value for the right side, which cannot be possible. Therefore, we don't have any trace in the xz plane. So, but traces in the vertical planes are the ellipses. If you write k, such that we have a negative value for the right hand side, because if you write this one to the right side, we will have a negative value here. And if you choose the variable of y such that we have negative value also for the right hand side, we will obtain an equation of the ellipse, you see, okay, in the xy plane. In the xz plane, sorry, we will write any number for y, and we will have ellipse for the xz plane. For the xy plane, we have hyperbola, and this is the graph of the given surface in this example. Similarly, you can see easily the graph of the given quadratic surface by looking at the table. Thank you very much. Send your questions to me by using the email.